Hi, this is Trev and welcome to my blog. Welcome to another episode of Tips and Tricks. This time round I'm going to show you guys how to MIG weld two bits of metal together. Sounds a bit boring. Yeah, I know there are 50,000 other videos on YouTube showing you how to MIG weld two pieces of metal together. But I like to do things slightly different and I like to add something in that nobody else is, and I've developed a way of keeping the distortion down whilst MIG welding. This is a request video. It's been asked many times and this is why I'm giving it you. I know that there are other forms of welding, but most of my questions are all from DIYers and car enthusiasts about MIG welding, so this is a theme I'm going to travel with on this video. I'm also going to answer lots of other questions that I've been asked over the last 6 months. So basically the top questions everybody keeps asking me, I'm going to try and answer in this one video. So I know it's going to be quite long, but I can guide people to this video and tell them that the answer is in this video. So the process I'm going to show you is really for very long joints. It's not for short joints, so don't bother doing it on anything short. Only do it on a long joint where you know that you're going to run into issues with heat distortion. Don't do it on a short joint because you're only going to add complications to the welding process and probably end up with more problems than you would have done had you not done it. I think you get what I'm saying. The only little caveat I'd like to poke in there is that this is really for classic cars that are made out of mild steel, not new cars, modern day cars that are made out of high strength steels. That's a completely different process, and we'll talk about that subject later on in the video. So let's answer the first question that you guys keep asking me. Trev, how do you clean up your metal before welding? Well, this is what I do personally. Of course there's going to be lots of people that are going to object to this video because they do it differently, and this is very much, guys, this is very much what I do. So you know, watch as many videos as you can. Lots of people do different things and they're all good. This is just how I find it best to do it myself personally. So I use two pieces of equipment. I don't use an angle grinder for cleaning up before I weld things together because I find that angle grinders take too much material off and you're just going to grind it thin just to clean it up. So I use a Scotch Brite clean and strip wheel, one of these purple ones. These are a bit more hard wearing than the black ones you can get. This is my favourite ever tool, this. The other thing I use quite a lot is I've got this mini air angle grinder which I've converted to a roll lock. So this is a roll lock mandrel in the end, and I've got a surface conditioning disc in here. Now actually I bought these from a company that was selling them on China. These are just knockoff ones, but they work pretty well and they've got the same kind of material as the clean and strip disc has got, and they do a fantastic job of cleaning off old paint and old rust. Okay, nicely cleaned up, all ready to be welded. Like I say, these things are fantastic for cleaning off old paint and bits of rust and stuff. They clean up rust very, very well. And so we're all ready to start welding it together. So the first thing I'm going to do, I'm going to show you guys a couple of ways of holding pieces together ready to weld it up, and it's a pretty basic process really. So these little welding clamps, you can buy these off eBay. If you put in a search on eBay welding clamp, these will come up. So very straightforward, clever little idea. This goes through the panel, one each side, then the peg goes through there, square hole, and then you tighten up the wing nut on the back and it grips it in place. So what I'll do is I'll set this up and show you it, how that works, and then I'll show you the other way I'll do it as well. All held together, nice and straightforward, happy days. These don't always work. Obviously you've got to have access to the rear of the panel. We'll talk about access later on. Another thing that people never mention, access, when they're doing these welding videos, so we'll talk about that a little bit more later on. There you go, nice and straightforward. So we'd all be ready to tack this together now. I could put a tack there, a tack there, tack there, tack there, then I could release the clamps, no problems at all, and then just carry on with the rest of the welding. It ensures you've got a bit of a gap there, because it's got the piece of metal that goes between, and I talked about the gap in the first MIG welding demonstration I did. You need a little gap there because it ensures excellent penetration right through to the other side. If you just butted it hard up and welded it together, you would need far more amperage running through your MIG welder to get the same amount of penetration, and that is only going to cause even more distortion than you would have doing it this way round. So always maintain that little sort of 1mm ish gap, and that'll help you no end. So I'll just show the other way quickly. So what I do is just get a little strip of steel and cut myself a couple of squares out of it. And what this does is this spreads the load. So when you grip it up with your C grips, another neat tip, these are vice grip made by Irwin. Fantastic grips, best ones I've ever used. I've done all the, you know, nipping down the market and buying some of them unbranded ones and other cheaper ones, and they're absolutely useless cheap grips, no good at all. So what you need to do is just square up this, get these little squares, just make sure they're nice and flat. I won't do that now, just to show you as a demonstration. So you just hold one underneath, put one on the top, get your C grips and just grip it up like that, and that holds the panel nice and level, so it's dead level. And I use this all the time. There's other people do it using these flash Glico clamps and everything else, and I'd like to get more into that myself, I really would, but there's only so many hours in the day and I can't research absolutely everything. So this is the way I do it at work. Getting stuff to line up it can be a bit of a fiddle, to be quite honest with you, but I don't have too many problems with it, and I find that the C clamps, I've got some big ones that reach right over as well, and this is what I normally do. We'll use these, like I said, these are fine as long as you've got the access. And the other issue with these is if the panel's got a heck of a curve on it, so if it's really dished, this has just got a very slight dish in this bit of scrap metal. But if it's very heavily dished, then these can create more problems because they don't, you know, they try and straighten things out. So whereas the pin grips, all the C grips, they hold stuff that's quite curved. So that's it. So let's get on. Let's tack this up first. So I'll tack this so it'll hold together, and then I'll show you my neat trip. So she's all tacked up, I'll take the clamps out, we'll move on to the next stage. I should just add that before you go any further, it's all tacked up, clamps are removed. Just make sure, guys, make sure that it's really, really nice and level and that it's perfectly in alignment. Both panels are perfectly in alignment with each other, and I'll just show you quickly. So this is the top surface, so this is the angle the MIG welder welded it from, and this is the back end, and as you can see it looks pretty much the same both sides because the weld has penetrated right through, because the wire's gone between, you know, there's nothing there, so that as the weld melts, it has to go in between the two pieces of panel, and this is why leaving the gap is so important, because you get that great penetration without having to have the welder ramped right up to get the heat to penetrate all the way through. So let's move on to the next stage. We're happy now, everything's uniform, everything's flush. Let's get on with the next stage, and I want to answer questions that keep being asked. I'm going to give you a few tips on MIG welder setup as well, because I think you're going to find some of that handy. So I'm going to throw some of that into the mix and it'll answer some of those questions. So let's get on with the next stage. So a few MIG welder basics. You've got your earth clamp. If you're welding, you obviously know all about this. So your earth clamp goes onto your workpiece. Your workpiece then becomes the earth. So thick cable, thick clamp, big piece of workpiece. So wherever you weld now is earthed. You got your torch. I know this is sounding a bit basic, guys, but stick with it. So you got your torch, you got your shroud, and you got your copper contact tip inside on the end that screws in. Now, express a little bit of MIG wire. Now, the contact tip electrifies the MIG wire on the end. That's why it's called a contact tip. So the MIG wire is being electrified from this very end, and as the wire comes out, it makes contact with the workpiece. The wire instantly melts and creates an arc between the workpiece and the contact tip. So as the wire is being fed out, it is arcing out, and it is melting and welding the two pieces of metal together, obviously. So that's the obvious part. Now the next bit is going to be a great little tip, really, for when you're doing fabrication, especially on thin material. So how can I put it? So like I said, we've got the thick cabling, we've got the workpiece which is thick, the clamp, everything's built to carry large amounts of current. The only thing that isn't is the MIG wire. Now the MIG wire is very, very thin, and so the distance between the workpiece and the torch can be quite critical as to how hot the temperature is on the arc. And when you must have heard about power cables losing current over so many miles. So you've got a substation and there's pylons carrying the electricity along. Well, it only goes for so long before there's a voltage, like a current drop along the cables, because the cables are losing so much current over a distance. Well, the same applies to your MIG wire. So as your MIG wire's coming out, so if I reel some out, let's just ramp the wire speed up. So there we go, I've got the wire speed out now. What I'll do is I'll attach this to the end of the clamp. So if I was to pull the trigger back now, there'd be a contact between the MIG wire and the clamp, and we've got a lot of MIG wire reeled off here. So we're welding, so this wire is going to instantly burst into molten metal, isn't it? Because we're welding. So look, it's not instantly melting as I pull the trigger back. So if I hold the trigger on, we might get a bit of a glow on. No, we won't. But I don't know whether the camera will pick this up. I'll put a bit more current through it. I'll put a bit more current through it, see if we can get it to glow. There we go, had a bit of a... Yeah, okay. So, the point I'm trying to make here, getting around to the actual point of the of what I'm trying to show you, is that the distance that you hold the torch away from the workpiece can adjust the temperature of the weld, and you can use this to your advantage. Now, you'll no doubt have seen many people saying you've got to hold it at an exact point, and they've got tips with castellated sections out so that you're holding it, you know, bang on the right distance away. And all this can be very useful for if you're trying to say do a plug weld or something like that, and you know that the weld is set up for the optimum, you know, you've got the wire speed right, you've got the current power setting right, so that you know that this castellated section is holding the contact tip a certain distance away from the workpiece to give you a weld that's consistent every time. So this is different. So what I'm saying to you is, you can adjust the power on your welder by reducing or extending the distance you hold the torch from the workpiece. So the further you pull the torch away, the less heat you're going to generate at the weld. And it's a very subtle trick, but believe you me, it works. It really does work, and I've been using this for over 20 years, this little trick. If you're welding something and it's very thin and it starts blowing holes, just pull the torch back a bit, get a little bit of distance, and you'll see, wow, the characteristics of the welder have completely changed. It's almost like you've just turned the power down. So let's talk about the power settings on the welder and the wire speed, and how you can adjust that and adjust it in subtle ways to give you a more desired effect. So here we have my MIG welder. It's just an old welder really. It's pretty good, reasonable quality, it does good quality welding. I'm just using a argon shield CO2 argon mix. People always ask me what my mix is. 5% CO2 with argon, so that must be 95% argon, 5% CO2, I'm assuming. So it's a mix. And the other question I keep being asked, so I'll answer it now while we're here at the spool end. I'm using I think it's a 15 kilo wire. It's just a standard mild steel MIG wire. I use 0.8 millimeters. This is what everybody keep asking me. Now, years ago I used to use 0.6, and I think from memory it's a little bit more flexible, 0.6, when you're dealing with car body work, i.e. it's thinner. There's quite a difference between 0.6 and 0.8 actually, and it's thinner, so obviously you're going to need to have less power to melt the wire. resulting in a cooler weld, I would say. But the main problem I found was if I had to make something up that was a bit heavy, if I was welding, say, 3 or 4 mil, it could be angle iron or some sort of, you know, this like hot or cold rolled steel that you can buy that you can make stuff up out of, little brackets and things like that. I was finding that when I welded it with a 0.6, I just couldn't get the wire speed up enough to absorb the weld. So, and the other thing that used to drive me absolutely crazy was every now and then, of course, the wire gets caught on the copper tip of the welder. When it gets hot, it splatters up and it sticks, and the wire sticks on the end. Everyone knows this that does MIG welding. It's a constant thing that happens. Don't really pay any attention to it anymore because it's not really an issue. But what used to happen was these wheels here that push the wire through, now you've got a tension spring here, but it's very, very difficult when you're using 0.6, especially on some of the older MIG welders, to set this up to a point where it would continuously feed the wire through nicely and also then slip the wheels when it got stuck on the ends. So what used to happen is you pull the trigger back, you'd be welding, it'd splatter back, it would stick to the contact tip, the MIG wire couldn't come out, and then it would all spool up inside the welder, and then you'd have to spend the next 10 minutes cutting all the wire out and then re-threading it all back through, only for it to do it again 5 minutes later. So this is why I scrapped using 0.6 and I've gone on to 0.8. I haven't got any issues with 0.8 whatsoever. I can weld the thinnest stuff, 0.7, no problem, all the way up to something that's 5 mil. So I hope that answers the question for you guys, because I really, really feel bad that I haven't got on and done a video. So this is why I'm doing this now, just to try and answer the questions. So getting on to the wire speed and the power settings. Now I can appreciate some of you guys have probably run off and bought yourself a welder for 100 quid and it's just got a few switches on there, and I'm sorry, but this isn't going to help you out much. Having said that, I have seen some reasonable welding done with some of these welders. In fact, a guy I worked with not that long ago bought one. He's got a little mini project he was going to do, and he bought this welder. I can't remember what it was now, 120 or 130 pounds or less, probably less than that. He bought it from, you know, one of these big tool places, and it didn't really have much in the way of wire speed and power settings. It was just a series of switches. I'll be honest with you, if you're thinking about getting into it, I'd probably throw about 400 quid at a MIG welder. Again, I'm not an expert at welding. I've spread myself very thinly, as anyone that I know that watches my videos. I've got a lot on. I'm doing restoring the old van, which is going to be a coffee van. So I'm doing sort of barista training. I like to play music as well. So, and then I do all the bodywork stuff and paint work as well. And it's, you know, I do my best with the time I've got, and no regrets really. Anyway, what am I talking about? Yeah, wire speed. So your wire speed. Now, I kid you not. Everywhere I've worked, and I've worked with a lot of guys now, and I would have said that most of them have the wire speed turned up too much. So if you're having issues with welding, if it's skipping about, oh, the welder won't weld properly, it's all skipping, it's a load of crap, that welder, I keep hearing this all the time. And I go over and I just turn the wire speed down. And I say, try that now. Oh, that's welding a lot better, isn't it? Yeah, you got the wire. Oh, I keep turning it up because it won't weld. Well, don't keep turning it up then. Turn it down. Why do you keep turning the wire speed up if it won't weld properly? So, if you're having problems, if it's skip, you know, it's no penetration, it's skipping. Turn that wire speed down. So that's a very valid point, I feel, because I keep witnessing this happening all the time. So if the welder's not welding very nicely, if it's not melting in nicely, you know, and it's just sitting on the surface, more often than not, you've got your wire speed turned up too far. Power settings, I mean, I've found that all these welders, I'm either on number 2 or number 3. This is a 180 amp model, and I've used loads of welders. My old welder I had before this one was 120 amp, and it welded absolutely fine, just the same as this one, because you're only welding the thin stuff. Obviously this one will weld thicker stuff than the old welder. So the more power settings you've got on a welder as well, it means that you can obviously go, there's more settings in between. But the point I was trying to get back to is if you're welding on number 3 and you're trying to set your welder up to weld, and you're finding that you're blowing holes on everything, and you've got it on setting number 3 because you feel comfortable using it on number 3. So you've got it set to number 3 or whatever you've got it set to, and you're blowing holes, right? Okay, first thing you want to do, turn the power down. Everything needs to come down, not up really. So the first thing you need to do is turn the power down. So turn the power down to number 2. I mean, it's sod's law, but I normally find that you want like a power setting in between, and some of the more expensive MIG welders, in fact our Tack do one, and it's got a variable power setting, so you can just turn it up and down like you could a TIG if you were TIG welding. It's the same on the MIG welder as well. You can turn that up and down. So that could be something you could look into if you haven't already bought a welder. So if you're on number 3, you're blowing holes, turn the damn thing down. Right, turn it down to number 2. Now you pull the trigger back and it's skipping. Next thing you need to do is turn the wire speed down. Like I said, turn your wire speed down. Try again on a scrap piece of metal. So you pull the trigger back, and what you'll find is, which could be quite frustrating, is you turn your wire speed down and it welds nicely, but you've got no penetration. Right, you need to turn your power back up. Turn your power back up. So turn your power back up. So you've turned your power back up. You're back into this situation now where you've turned the power back up and you're blowing holes in it again. Right, first thing you need to do, if you're blowing holes, so number 2 wasn't strong, powerful enough, you've gone back to number 3, you're still blowing holes. What do you need to do? You need to turn your wire speed up. So you turn your wire speed up, the more wire that's coming out at the end, the faster it's coming out, the cooler your weld's going to be. Okay, so you turn your wire speed up. Now then, if you turn your wire speed up and it's kind of welding okay, but you're still not entirely happy. Now this is where, or you've got some inconsistency with the thickness of metal you're welding or something, this is where you can now utilise pulling the torch away from the workpiece. So you just need to reduce the heat slightly, because you've got it on the optimum power level, so it's penetrating well, but it's just a little bit too powerful. So what you can do is just pull the torch back a little bit, pull it back, and you'll find that the weld instantly becomes a lot cooler than it was before. Top tip, guys, top tip. Next thing I talk about is your gas, where you've got your gas turned up or down, depending on how much gas is going to come out at the end of the torch. Now, another huge thing I see, most of the people, big mistake, mind you, most of them aren't paying for the gas, so they're not bothered, but the first thing you want to do, I would have said, is turn your gas down. Now, I haven't got a regulator that tells you how much gas is coming out. It only tells you what's in the bottle on mine, and I can't remember exactly the setting you need, but I'm telling you now, you want to turn that gas down so that it's just a whisper of gas coming out. And most of these guys I work with, they have the gas coming out like it's an airline. You just don't need that much shielding when you're MIG welding, particularly on car bodywork stuff. You just don't need that level of gas coming out, and you'd be amazed at how much you can turn the gas down and still produce beautiful welds, and then conserve easily half of your, I mean, if you're putting a bottle on it, you know, regularly, and then you turn your gas supply right down so that it's a lot less than it is currently, you'll find that your welds are just the same, but you're only using a fraction of the gas or half of the gas. Easily half, no problem. Most people have got it set up double what it should be, no doubt about it. So turn the gas down is another tip if you want to conserve your gas. Safety goggles and reading glasses, an absolute must. Many of these safety goggles come UV protection. I think these are 99.99% UV protection. So if you've got these goggles on and then you get flashed by the welder, you won't get arc eye. Same as if you're wearing your reading glasses. If you need reading glasses, wear your reading glasses, because they'll give you some extra protection whilst you're welding. I've had arc eye several times and it's no fun, believe me. And I think I paid about £3 for these from B&Q, and they're UV protected, so I always put these on. My welder has got this it's got this problem where it holds a slight residual current, and so when you put it on the work, if you accidentally just touch the wire on the workpiece, even if the trigger isn't held back, it always gives you a little bit of a flash. So let's get on with welding this up, and what I'm going to show you next is my tip for creating way less distortion. So I've got this 3M Spirit wiper cloth. It's like a lint-free cloth, it's not tissue based, and it's designed to not release any fibres when you're using it as a panel wipe to wipe down for paintwork. So what I do is I get this cloth, and I like using this stuff. Like I say, tissue's no good, so what you do is you cut it into strips. So on the roll, it's rolled along, because you can see the perforations along this edge, so it's rolled that way round. Now this way, round, it's got no give, so there's no stretch, and the way it's woven is that this way round it'll stretch quite a lot, which means that when you put it on the panel you can bend it round corners. Yeah, you get what I'm saying? So what we're going to do is we're going to soak this with water. So I'm going to soak it with water, and we're going to put it each side of the welded area, and then this will act as a heat sink for when we're welding. So I've got our workpiece, I've got some tap water straight out of the tap. Soak the cloth in the water and give it a little bit of a wring out. You don't want it too wet, because you don't want it running into the weld area, because all that's going to happen is it's going to turn to steam and you're going to end up blowing holes in your weld. Now, there is a kind of school of logic out there that says that you shouldn't get water near something that's going to get very hot if it's going to get welded, because it can cause an issue called hydrogen embrittlement, where the hydrogen in the water becomes fluid and is actually absorbed into the material. But I've had a chat to a few people that are in the know on this kind of thing, and they've basically said that it isn't going to affect what you're welding, because it's just mild steel, and it's more to do with welding more exotic materials, and also much you know, harder steels which have got a greater carbon content, and this is what helps or causes the hydrogen embrittlement. And on mild steel, you're pretty safe bet that this isn't actually going to have an effect on it. So you just put your 2 towels across like that. I normally get them a little bit closer than that, actually, about that far away. Now the other thing that's available on the market is sprays that you can spray on things, and I find that they just kind of make a bit of a mess really, and then they end up getting, again, end up getting in the weld. And going back to the old talking about the hydrogen embrittlement situation, I've also done a bit of research and found 2 data sheets on 2 different products that are sold, and their key ingredient is water. So there you go, they're basically water and a product that's used in hair gel. Now I'm not suggesting you use hair gel, because there's going to be other chemicals that are in cosmetic products that are going to give off some nasty gases, I would have thought. So there you go. So a couple of bits of cloth on there like that. I'll get it a bit closer, you can see exactly what I've done. And what I've done is I've smoothed it out, because you get air bubbles, so you want to get good surface contact with the steel so that you drive all the air out. And this has now created a heat sink which will absorb the heat. It will just wick the heat straight out of the welded area. Obviously it's still going to get extremely hot, and the reason that a lot of people say not to use MIG welding when doing car body work is because the welds are a lot harder than if you were going to TIG weld or you were going to gas weld. But one of the main reasons they say this is because they don't use things like angle grinders to grind the weld down, and I'll talk more about this later on in the video. So we're all ready to weld up now, so I'm going to weld this across. I'm going to do as I did in my last MIG welding video, so some of these parts are going to seem a bit tedious to you, but what I'm going to do is I'm going to do a process called skip welding, where I will weld there first, then the next one I will do is up here, and then one there, so I'll be going in between the welds, and I won't necessarily do it uniformly or stagger them and space them out. And the whole point of this is so that you put a weld there, so it's very hot in that area, and then I'll move over here where it's cold and I'll put another weld. By the time I come back to this, the heat will have dissipated and be gone, and you know, there's no heat there. The whole point of this process is to keep the heat to a minimum, because heat is what distorts the panel when you're welding something. So let's get on and weld it up. So something else that I'm doing that's worth mentioning is I will set the welder each time. So I'll pull the trigger back to spool a tiny little bit of MIG wire at the end, and so I've set the welder, hold that so it's close or practically touching the workpiece. I've already got it a set distance away, and then I'll just pull back the trigger. After you've done a few welds, you will see the cloth drying out, and then it's losing its effectiveness. You just get the leftover cloth and get that well wet, and then you can just lightly dab, and you'll see instantly that it absorbs the water straight back in. You don't need to take the cloths back off and start from scratch. you can just simply dab them like that and they're set again, ready to do some more welds. Okay, so I've welded the area as well as I can. What I'm finding is that there are a few little holes that I can't get to because the welds are standing up a little bit too high. So what I tend to do at this stage is I tend to grind the welds off, get them off, and then I just fill in any ones that are left afterwards. I know this is a bit tedious, but this is the kind of thing you've got to do when you're going to MIG weld stuff. So one of the other questions I'm going to answer now that people keep asking me is about grinding the welds down. What do I do about this? Do I use a flat disc? Do I use a belt sander? Blah blah blah. No, what I use is I use an angle grinder with a flat fibre disc. I don't like using flat discs for grinding down welds because they're a little bit vague. They're great for cleaning stuff up, maybe even if you're going to weld. You know, I'd rather use a fine flap disc rather than this, because this takes material off. But for grinding welds off flush, I find that the fibre disc is far better because it is flat. And the discs I use are quite expensive actually, but they're brilliant, and they're brilliant because they are so sharp that they take the weld down, because MIG welds are super tough, as you must have heard if you've watched other welding videos. So you need something that's going to cut through it, and these really do. These are the best discs I've ever used. They're 3M Cubitron 2. They do a Cubitron disc, but this is an improved disc, and the particles on there, as they wear down, they actually shatter and form a new cutting edge which is as sharp as the disc was when it was new. So these last, I mean, these outperform the average disc, I would say 4-to-1, no problem, and they're certainly not 4 times the cost of a good quality disc. So this is why I buy these, because they last so long. They are expensive in comparison to a cheap disc, but hey, you get what you pay for, don't you? So what I'm going to do is I'm going to grind this weld down to reveal the little holes that I've missed. Let's not get too anal about these tiny little bits you've missed. I was going to say anal about holes then. Nice one. Because if you're going to MIG weld anything and you're going to do it like this, you will never ever seal it up with weld. You just won't do it. And if you don't believe me, MIG weld a piece of pipe, and then power it up with your airline, and it will just hiss out everywhere. If you've done it with this method, you can't do it. So what I always suggest is do the obvious stuff. Don't beat yourself up about the odd tiny little pinhole here and there, because if you brush some epoxy primer both sides of it, and you don't thin it down so it's nice and thick, if you brush that in and then leave it for a few days to fully cure, I mean, epoxy takes about 7 days in total at room temperature. If you brush that into your weld, that'll be completely sealed up, and it'll be impervious to water as well. Far better off than doing your head in trying to get every little pinhole, because you won't anyway. You can't do it, it's impossible. So I'll grind this off, and then I'll weld the little pinholes up, and then we'll see where we are. Just flip it over actually. I'll flip it over, I'll take the cloth off, I'll flip it over so that hopefully, if I get the camera to zoom in, so you can see that we've got excellent penetration all the way back on the back of the panel, and you can also see no distortion. See? No distortion. I say no distortion. I'm being slightly misleading there. There's no distortion in the panel after the weld. So where the weld is, it will have drawn in very slightly. But impressive stuff, guys. I'm going to grind this off then, and then we'll come back, and then I'll perhaps finish up the inside as well. What I normally do on the inside is I normally use my 20mm belt sander to go on the inside if I want to get that flush. Obviously if it's behind a box section and there's no access, don't beat yourself up about it, guys. If it's just going to be blathered in under seal and you can't see it, then don't even grind the weld off, because that weld is strengthening the joint as well. If you grind it off, you've got less welded material there. So I'll grind this off and we'll come back. Okay, so all the welding's finished. As good as I'm going to do this piece anyway, this is only a test piece, this isn't on a car, although I'd be quite happy with that, to be quite honest with you, for most jobs that I'd be doing. The back side looks pretty good as well. I've just ran the grinder along that. I've got a couple of tiny little holes, oh, really tiny, or maybe even just small recesses really, rather than holes. So that's it. This is how it is. Honestly, I mean, I have just put the grinder over it, haven't polished it up, as you can see. It's just as it's come out, and you know, I can bend this, I can bend it, it's not falling apart. They go on about MIG welds being hard and brittle and, you know, everything else. I mean, this isn't going anywhere, is it? I'll just show you one last thing. Got a couple of little holes around it, because this is just an offcut from another project I've done, and just another little neat one. I've already done a video on this, but I just slipped this in, as a lot of people probably wouldn't have seen the other video. Just got a piece of copper, you got a hole like that, you want to plug that hole up. You know damn well, if you get your welder and you weld that hole up, you're going to end up with a massive great big bead the other side. You're going to put tons of heat into it. Again, lots of heat distortion. You got a nice chunky piece of copper. This is just an earthing strap off a spot welder. So I'll just pop that behind there like that, and then I'll grip it into place with my pin grips, and I'll just weld that up. I'll show you how well it comes out. So what you can do is you can aim your MIG. You can put a bit of power on this as well, because most of the power is going to be going into the copper. So you can just turn it up a little bit if you want, and make sure you get really good penetration. So yeah, I'll just weld it into that hole there, and we'll see what it looks like afterwards. Okay, plugged up. Release the copper quickly. Most of the heat will be in that copper, not in the steel. So that's done. I'll just grind it off quickly. Okay, so that's where the hole was. Flip it over, you can see the reverse side. You can see that I haven't ground it off at all on the back side, and it all remains beautifully flush because the copper sat against that in a flush way, and you welded it to the copper, and then it puddled out till it hit the steel both sides. Plugging up that hole without any drama. What a lovely job. The other thing I'll just mention quickly is finishing up, polishing up. If you want to polish the panel up, don't get too carried away with this, guys, because you'll just grind it thin. But what I do, I've got a variable speed angle grinder with a DA pad, adapter pad, mounted onto it, and of course what I can do is I can polish the steel up by putting, I just normally start with an 80 grit disc, so I put an 80 grit on there, polish the steel up, and then I can go down to a 180. Never go less than 180. I mean, you're just getting it mirror finished then. Okay, the repair area has been polished up with a variable speed angle grinder. I knew my outcome before I started. As I said, it would draw it in very, very slightly along the welded area. You could probably just see a tiny little bit there. The rest of the panel remains pretty undistorted. I'm happy with this. I would just DA that down now with a 180 disc to key it up, because it's too shiny now, and then I'd epoxy it both sides, a little slipper filler along there, completely invisible repair. Happy days. So okay, We've all seen videos where they've endlessly gone on about how tough MIG welds are, and they are tough, a lot tougher than certainly gas welding is. And let's just put it to the test and see how brittle now this panel is. I've got a flat block and I've got my plate, and this has got a very slight curve to it. Let's just try and straighten this out. When I straighten it out, we'd expect it to see it split wide open along the weld. Kill him! Kill him! Yeah, it's still looking pretty good actually. Well, so I can actually bend it along the crease. Well, oh, I've got it to split now. It has split now. I got a little split just opened that right on the weld, so there you are, but that's taken some battering to get that to do that. I'm going to perform another strength test here. I guess you've gathered from the last demonstration that I'm not exactly scientifically accurate, but I think it gives you a pretty fair idea as to what happens with these materials when you do things to them. So what I thought I'd do is get some mild steel and some carbon steel. I don't know the grade of this carbon steel. All I know is that it's much tougher than the mild steel, and I know this is mild steel. So what I intend to do, I've got 3 samples of each, and they're both the same approximate size, so they're both, the thickness is the same and the width and the depth is about the same. Pretty close, and close enough I think for what I want to do here. I'm going to do a very simple test where I'm going to put these samples in a vise with a pair of mole grips and bend them backwards and forwards until they snap. But first, what I'm going to do is I'm going to put 2 aside and leave them as they are. The remaining 2 will be annealed and also quenched, so we can tell what happens, what effect these heat treatment processes have on the steel sample, dependent on their properties. This is going to be quite an interesting little experiment, I think. So the annealing process, all I'm going to do is I'm going to heat the samples up as hot as I can get them, and keep them there for a prolonged period of time, and then allow them to cool down very slowly. Actually allow them to cool down in a heated place, and then let them cool right down as low as they can go, and then keep removing them to a slightly cooler place until in the end I allow them to be in the normal atmosphere. Then this will allow them to cool down at the slowest rate possible. What I'm going to do with the samples that I'm going to quench is I'm going to not heat up the entire sample. So I'm going to do kind of, I suppose, what would happen if you heated up something, if you were doing, say, a plug weld or something like that. So I'm going to heat up the central section of the sample in a strip. I'm going to get that quite hot with the welding torch, and then when I've got it nice and hot, I don't want the heat to dissipate too much into the whole sample, so I want to try and get it done as quick as possible. So I'm going to get the central as hot as possible, and then when it's as hot as possible in a strip in the shortest time possible, I'm going to then plunge the sample straight in to cold water, and then we can do our test then to see what happens, what changes takes place dependent upon the type of steel sample we're working with. So I've got the steel samples ready, obviously carbon mild, and the different types here all lined up. I'll put equal spacings, so I'm going to mount it into the vise up to there, mild grip it to there, so we've got an equal amount on each one, so everything's fair. I'm going to be wearing a face shield just in case a bit of splinter comes off on the old carbon ones, because this is the ones I'm most concerned about. I may edit this down slightly. It could get a bit tedious to watch me wiggling a mild steel backwards and forwards 20 odd times, or however long it's going to take for that to break. So I may just edit it down and then just do a quick tally up at the end. But I'll put plenty of info into this, so you'll see the detail. Okay, so this is going to get a bit tedious, guys, so I'm going to edit this right back down, because this is going to be like watching paint dry, isn't it? So we'll zip fast forward to the results. Here are the final results. We've got high carbon steel this side and mild steel this side. We don't know the specific grades of either product, but this is sold as mild steel, but we don't know who manufactured it and exactly how much carbon they put in it. I know this is high carbon steel because it's so much stiffer than the mild steel is. So getting back to the results and the test, I realised it wasn't exactly a scientific accurate test. It's just to give us a guide. I know there's going to be people that are going to split hairs over this, but I think this is just giving us an overall view of the different properties of each type of product. So yeah, the bend test as well. I also realised that the first bend was only a half bend, and then the second bend then would have given us the full bend, and the full bend was approximately 130 degrees when measured on a protractor. So the high carbon steel 6 bends and the mild steel 17 bends untreated. So this is the untreated. We can see there's a big difference between those two in properties. So sticking with the high carbon steel, once it had been annealed, it went from 6 to 20, so it jumps up a lot. This was much easier to bend. In fact, I couldn't believe how much easier it was to bend. So something to bear in mind: if you're going to heat up a piece of high carbon steel, you heat it up, you are going to vastly change its properties when you heat that stuff up. When it's quenched, even more worrying. I put lots and lots of pressure on that sample and it wouldn't even bend. It didn't try to bend, in fact it just sheared off. Although it did take a lot to shear it off, there were no second chances. It just broke and that was it. The mild steel, so the mild steel untreated 17, once it had been annealed it jumped up to 25, and then it jumped from 17 down to 12 once it had been quenched. I did expect these figures to be slightly closer together, but of course we don't know exactly what grade it is. And also you can see how more uniform these numbers are this side than they are this side, which is basically what this little experiment was all about. So I'm going to blow your minds now slightly, and I replicated the test on a piece of 20 gauge steel. So 20 gauge steel is 0.9 millimeters. So this is 2 millimeters. These samples were 2 millimeters, and I also replicated the test on 0.9. So with the 0.9 samples, the score jumped on the bend test. It jumped from 17 up to 216 just by reducing the thickness of the material by approximately half. So we can see that it's far more ductile the thinner the material gets. The quench sample performed very well as well. It still performed 167 bends. So we are talking a piece of heavily quenched mild steel, still going through 130 degree of bends and still did 167 on my bend test. Obviously the tighter the bend you try to put it through, the lower the score would be drastically, but it just goes to show how malleable the product still is even after it's been heavily quenched. Obviously I'm not advocating that you heavily quench any product, even mild steel. Just use it to take that residual heat out, to stop things from warping and bending. As you saw when I smashed that sample up, it withstood a hell of a battering, even though the heat had been wicked away from the weld. I always almost think about it as well a little bit like spot welding. So when something's spot welded together, the metal around it remains very, very cool, and the spot weld has to get to a molten metal stage, so it's extremely hot in the weld area while the other areas around it remain quite cool. So there must be like this difference, like I've done here. There must be that difference, and of course the metal around it still remains quite malleable. One last point I'd just like to say whilst I'm wrapping up, when I'm talking about performing these procedures, we're talking about mild steel panels on classic cars. We're certainly not talking about modern cars. And we're talking about outer skin panels, because A posts, B posts on say newer classic cars, they may actually have some higher carbon materials in, so just be wary of that. Also, we're not talking about chassis, and we're not talking about suspension parts or anything like that either. We're just basically talking about outer skin panels that are definitely made out of mild steel whilst performing these kinds of operations. One last point I'd just like to make before I wrap this up is that any repair work that you perform on a car is a repair. You will never ever put that vehicle back to what it was originally once the manufacturer's done, and you are repairing it because there's damage there. It may be rust damage, so you're wanting to replace that rusted out item. Now the rusted out item is going to be far weaker than anything you put on. Any compromise that you make to the structure of the material putting in is going to be some kind of compromise. Whether you're bashing pieces of metal around to form them into a panel, you will put some kind of compromise into the brittleness of the structure of the metal, because you've work hardened it. The same as if you're going to weld it, then there's obviously going to be a strength compromise, and just bear all this in mind. It's all compromise and it's all common sense. Just to quickly answer another question that keeps on coming up about stepped joint that I've shown in some of my videos. Basically what it is, it's called an edge setter or flanger. Flange. I had to say that because the mini boys love saying that so much. So I've got an old Sykes one here. I've had this one over 20 years. This one's a little bit deeper than the Mickey Mouse one I bought off eBay, which crap really, but it's okay. It does a shallow one, and it's a hole punch the other side, but it's so badly made that it's a real effort. Now it's jammed up, but it makes a 4mm. I think it's a 4mm. 4mm, yeah. So that you can make holes in a piece of metal, and then what you can do then is, obviously, if you were doing a standard lap joint, so you're putting out like that, then you could then weld through that hole instead of using a spot welder to recreate a kind of spot welded joint. So you do a series of holes along this panel, sort of, I don't know, sort of 20 centimeters, 30 centimeters apart. And then if you putting two pieces of metal together, joining them like that, like the edge of a sill or something, you'd have them like that, gripped up, and then you'd weld through to the panel underneath. Just will say one thing about this. The hole is so small on this that really you need to be kind of using this type of weld lead down, so that the gravity draws the weld down. I have found that if you're trying to weld uphill, it's very hard to get penetration through, and you end up with no weld on there at all. So that's quite a worrying aspect for me. I prefer to drill a 6mm spot weld with a spot weld drill, 6mm hole. Now I'm quite happy to weld on the vertical rather than, you know, welding directly down. So that's that. So the other side is a joggler or an edge setter or a flanger, and what it does is you go along the edge of the panel like this. So you go along. I'm just doing this quick so it might not look very good. There you go, and it's put a nice little step. Don't know if you can see that. Put a nice little step in the panel, and then when you mount it to another panel, so this could be your lower half, this could be your lower half door skin, you see? This section here could be your lower half door skin, like I've done in another video. So this could be your skin, this could be the existing door skin, and then of course you lay this over like that, and you have a flush joint. And what I like to do is get this, I don't like to have it right up in there, I like to have it backed off a little bit, and then I'll just spot weld with the like I showed you earlier, a tack weld along in this recess here. And what this does is it forms a much more rigid joint than if you were doing a butt to butt joint. And then of course you get all the distortion, it sucks the door in. Classic thing people do, they weld it along because they want it nicely butted up. It's so much nicer to butt weld things, but at the end of the day, when the time's against you, and it depends what the car is. A lot of these classic cars come in and they're absolutely already completely full of filler already, and I just think, well, if I put a bit of filler along a stepped edge afterwards, a little bit of filler just to finish it off, and the rest of the door is already completely filled up with filler, I can't really see what the problem is. The big problem with this kind of joint is the reverse side, because the reverse side has now got an edge that moisture can creep up into. Then you're in this situation where it's going to rust out between the two pieces of metal. So what I always do is when I come to a frame section, so I'll come to the edge of the frame, what I'll do is I'll do a true butt joint over the frame on the last little bit. And what that does is that gives me the beauty of the lap joint all the way along where the door's weak. So I'll have that strengthened joint all the way along, and then at the end where it's supported by the frame, I'll then TIG weld it along that last joint, that last, however deep, basically however deep the frame is. So if the frame's an inch deep, go an inch and a half so that you're covered. And then what you can do is you can then go from the inside of the door, you can primer it first, so key it up, primer it first on the inside. I keep saying epoxy primer because it's non-porous, something like that. So primer it inside, let that go off, then lightly key along the joint and get some polyurethane adhesive and seam sealer, and then seal that joint in so that moisture can't get between the two panels. And you're not really going to have a problem then with this moisture creeping up. It's far more likely to rot out again where you've lipped it over the frame than it is going to be along that joint. I know this because I've seen cars come in that have had these kind of repairs done, and that joint is absolutely mint still, and then it's gone again on the lip. So experience tells me that sometimes it's not obviously it's not preferable to do this overlap thing, but sometimes I'll tell you what, it saves the stress levels rather than trying to butt it up, especially if you're, I mean, it all depends what it is. If there's big time constraints, it depends how much the customer wants to pay, etc, etc, and what the condition of the car is, of course. How long you want to spend welding the bottom of a door on. Do you want to spend, you know, do you want to spend 2 hours lap jointing it over? So lap joint it over, get it done in a couple of hours, or do you want to spend 2 days butt welding it up, planishing all the way along? It's up to you. You make the choice. Okay, so this is all going on far too long, but I want to cover all bases on this video to the questions I keep being asked, so as quickly as I can. Trev, being brief, I don't think so. People keep asking me, Trev, what forms of welding do you use? Trev, why don't you TIG weld? Trev, why haven't you gas welded? Etc, etc. The main reasons I haven't shown you a lot of other forms of welding is because of the fact that I haven't got these welders myself. So this is my own private workshop, and I've only got a MIG welder. I've got a gas welder, but it's using a butane acetylene mix, which means that it's okay for brazing but not great for welding. At work I use a mixture of TIG welding, MIG welding and gas welding. Now, there are 3 branches of influence, I would have said, that people watching YouTube videos are going to get their information from. So this is going to be a completely honest representation of how I see things. This is just my own subjective opinion. This isn't a definitive welding guide. It certainly isn't. This is just the things I've come to, made my own opinions, which work well for me. I've got a job to do, and I've got to do it as best as I can. So, there's industrial welding. So you're going to be watching videos on people that are in heavy industries, welding up stainless steels and lots of exotic metals, and welding one type of metal to another different metal, etc, etc. And these guys, they'll cover a broad range of topics. And then there's the car side. So you've got the coach building, and you've got accident repair. Now, up until 5 years ago, I worked in the accident repair industry. I have worked on classic restoration before. I ran my own business for 7 years, but at the time I was basically buying in wings and stuff for Morris Miners. I may weld in the occasional lower half door section or something. I certainly wasn't fabricating my own panels or repair sections then. And then I went back into the accident repair industry because I've been in and out a little bit. And I worked in the accident repair industry for about 15 years straight. And I came out about 5 years ago. So just to tell you about what they would use in the accident repair industry now, as opposed to 1986 when I started. So 1986 I started, and the first guy that welded a quarter panel on, I helped. I actually gas welded the joints on a quarter panel back in 1986. And that sort of fairly quickly fizzled out with people using MIG welders more. So basically we just MIG welded everything together all the way up until, I would say about 2007. And then something took over where everything's got to be British Kite Mark overseen, approved. And the reason being is that modern cars are made out of high strength steels, and there's no stamp on the panel to say what kind of steel it is, and there are over 200 different types, variants of high strength steel. The inner core normally being made of a product called boron steel, so the passengers will be surrounded in like a kind of roll cage, if you like, that's all on the inner pillars. You can't see any of it obviously from inside the car, because it's inside the sills. So all the inner sills and all the A post, B post, C post will all be like a boron steel shell wrapped around you. Amazing stuff. Watch some demonstrations on it. You can get a piece of boron steel and you can pound it with a sledgehammer and it won't bend. It is extremely heavy stuff. And then what they do is they surround the car in softer steels, and they also build in crumple zones that when you have a crash, it absorbs the impact. So the car kind of folds up around you until it gets to the boron steel, and then it says, that's it now. You're not coming any further. Got to the boron steel, it's taken the impact out of the crash, and it's got to the boron steel and it won't move anymore. And the reason they do this is for fuel economy, because they use high strength steel on the outer body panels now. So the outer body panels are high strength steel, the inner is boron. This means that they can produce a lighter, stronger car. Another myth I'd like to bust is that old vintage cars are far stronger than new cars. That is a complete myth, guys. It's the other way round. Definitely the other way round, because old classic and vintage cars were all made out of mild steel. Practically the whole car all the way through is the same product, and when that's hit, it folds up far more than modern day cars. So there you go, folks. If you're really interested in safety, don't drive a classic car. The only thing is, if you don't drive a classic car, if you have a crash and you check out when you crash, you don't look as cool, do you? Break on through, break on through, break on through to the other side, break on through, break on through. So that's a basic overview of high strength steels and mild steel. I could go on, but I'm not going to. Let's wrap it up. So getting back to the whole welding side of things, as you've just seen, I've MIG welded a piece of mild steel, and the mild steel is quite soft, so it's accommodating, and it kind of gives a little bit around the weld and allows the weld to sit there. And it took a pretty good pounding until it finally gave out. But to be fair, it did give out along the weld, which shows that it is more brittle than other welds. The point of what I'm trying to say is the industry has suddenly realised that they're using all these unusual materials that haven't been around up until quite recently. I think about 2007 on, it's all, you know, there's a fair chance you've got high strength outer body panels on a modern car from about 2007 on-ish. Don't quote me on this, guys. I'm just trying to give you a bit of a guide here. So what the industry did is they had to think of new ways of holding these cars together. So what they do a lot of now is riveting and bonding to save the heat. So a lot of panels are riveted, bonded, and also panels that are traditionally welded along the joints. They do a lot of MIG brazing, which is at a lot lower temperature, because they have found that when they did shear tests and they MIG welded it, it just broke each side. Not actually on the weld, but apparently it broke a little way back from the weld, but the heat from the weld had actually made the metal extremely brittle, and this is probably because of the high carbon content in the material. And when you heat something up and cool it down fast, which is what MIG welding is, this is why it's brittle. You MIG weld something, is going hot cold very quickly. When you gas something, you're heating it up, the panel's getting red hot, all that heat's flowing into the panel, it's all getting hot, it's all getting hot, and they finally get it up to the optimum temperature so that you can start fusing the two panels together, or start putting some filler rod in it, or whichever method you're going to do. And then you take the heat away, and then it slowly cools down the whole panel. The whole area is all hot, so it takes a long time to cool down. And this is why, you know, fast, hot, cold, it's going to be a lot harder than something that's a slower process. And this is why gas welding is so much softer than MIG welding, and TIG welding would come, I would have said, somewhere in the middle, because you could do a quick flash with a TIG weld, or you could do a prolonged weld, etc, etc. You get what I'm saying. So the accident repair industry are using MIG brazers using a silicon bronze. Yeah, silicon bronze. QZ, what do they call it? QZ3 we used to use, which was it was a licensed wire, so it's kind of guaranteed, you know. So you had to use that because British standards told you, and that was coming in at about 300 quid for a 10 kilo roll. Happy days. So anyway, that happened. Then we all had to sign our names to every job we did, and then the spot welder was Bluetooth to a computer, so it counted every single spot weld, and you had methods, etc. And it all started getting a bit heavy, and there was also this corporate manslaughter issue come in, where you put your name on it, the company doesn't get prosecuted, the employee goes to prison. Now this is what happens. So on top of that, and on top of you know, ridiculous management, I decided to bugger off. So I did that, and then I fell into this restoration job. So I've only been able to take all my experiences with me. So as I was saying, the 3 branches. So then you've got the coach building side. Now the coach builders, they're making complete panels from scratch. They're making very, very large panels, and everything's very open. And they're basically making a skin panel for like a whole wing or a whole car, whatever. And the key, and this is what nobody talks about, is access, because they can get access behind the weld. So when they gas weld something or TIG weld something, which it's going to create heat distortion a lot less than you would expect, actually. And I'll show you some videos on that soon. But what you do, see, is you do your weld. You get your dolly behind, and you planish the weld out, and you planish the weld out because it's heat shrunk. So like I said, showed you my heat shrinking video, when you get metal hot in one spot, the cold metal around it forces that expanded softer area to shrink in on itself, and then when it cools down, it's lower than it was before. Same with the welder. You put a weld in there, it gets very, very hot, and then it shrinks the area that you've welded. So then you have to expand it again by putting a dolly behind it, bashing it with a hammer, and then that stretches the metal, because when you're bashing it, you're making it thinner and longer, so it stretches it back out, and you can do beautiful joints so that everything's lovely and smooth afterwards. And if you do it right, I mean, if you use some filler rod as well and fill it in and then mess about filing stuff off and everything, you can get it so that you can't see the joint. And I would have said that in a nutshell. So when people ask me, why don't I use TIG welder? Well, the main reason I don't use my TIG welder at home is because I haven't got one. I use it at work, and I'm using it more and more these days. I also use a bit of gas welding at work, and I obviously use a bit of MIG welding at work, and it all depends what I'm doing. Horses for courses. You play to your strengths. So you know, I'm not as experienced as some of the guys using these kinds of welders. So what I do is I use the welder best suited to the job, to me, and you should do the same. I mean, it's far better to have a decent MIG weld than a really bad gas weld, if you know what I'm trying to say. And the other thing as well, which I'd like people to comment on, if you would please guys, I actually know professional coach builders. I've had a chat to some of them, and there's some that use TIG weld, will not use gas weld, and there are some that use gas weld, will not use TIG weld. So there you have it guys. Even the people, even the pros running their own shops and their own businesses don't use the same methods, and fiercely disagree with the other side. So I'm trying to take advice from these people. So what I do is I use what's best for me. I mean, I just put not just a couple of years ago, probably now, must be, I built a windscreen surround, complete windscreen surround all the way for an old Citroen SM, and I had to weld all the way along the roof panel, which was like a piece of tin foil like that, and I welded it all the way around using my heat sink method, and that roof was absolutely fine afterwards. Now, had I come to use the TIG welder, I'd have had to sustain the arc to get it to flow and everything else, although TIG welding is a lot cooler than MIG welding, but it depends how you're going about it, you see. Because I use my heat sink, and I was just tacking, spreading it out, I've ended up in a situation where I've got no warpage along that roof panel. Had I used a TIG welder, and I could have got to it, I could have TIG welded it, planished it up, beautiful. Problem is, roof panels on the car, you can't get to it. It's all encased, it's all enclosed, it's all closed in. If you can't get to the back side of the welded area and planish it out, you're going to end up in a situation where it's distorted in and there's nothing you can do about it. And this is what people never talk about, so this is why I'm talking about it now on my video. I plan to get a TIG welder for home, and I also plan to convert my gas welder to pure acetylene, because pure acetylene is far better than the stuff I use, but I only really use it for heating stuff up and for doing a bit of brazing every now and then. But I'm saving it for a TIG welder. I don't want to just get a standard DC machine. I'd like to get an AC/DC machine so that I can do the aluminium, because I haven't got any space here, and the AC/DC machine, although it's much more expensive, about £1,000 or something like that, it's only an inverter one, it's not a 3-phase or anything stupid, it could probably live on top of my MIG welder, so the footprint's going to be the same, and that's why I don't want to get a steel one, just a DC one. So without doubt, one of the most asked questions is, I'm a complete novice, or I'd like to get into restoring my own car. I bought a car, it needs some welding, I've never welded before, or I've got a welder and I don't know how to use it, etc, etc. Now this is the question I keep being asked: what kind of welder do I need to go off and buy? Now there are kind of three choices really when it comes to classic cars. You're going to be able to MIG weld stuff, you're going to TIG weld stuff, or you're going to gas weld stuff. So what I would say is, it's all about you as a person, and it's all about your project that you want to do. What are you actually trying to achieve is the first question that you need to ask yourself. Don't ask me, don't ask anyone else's advice. What you really need to do is think about what you want to do yourself. Now, I would say if you're an enthusiast that wants to get into coach building, so you want to get into coach building, you want to be making your own, complete wings and all the rest of it, massive great big sections of material, then you're going to have to get pretty serious, guys, and you're going to have lots of equipment like English wheels and all the rest of it, and you're definitely going to want to learn how to TIG weld and how to gas weld. And I mean, there are people in that industry that can't really agree with each other, but they're basically the two kinds of welding that you're going to want to look into, is TIG welding and gas welding. If you're going to be doing coach building, i.e. making massive panels, complete panels, all from scratch, then that's the way you're going to go down to. Now, if you're going to be like most people that ask me the question, then you'll have bought yourself a 1960s, 70s, 80s, 90s car, classic car, that needs it needs a bit of work. It might need a wing, and there's a hole in the sill, and etc, etc. So basically you're patching up an existing panel. You're not getting into the heavy end of fabrication and manufacturing your own panels. You're just going to make a little repair section and put it in there. And I would say, if that's the case, then you can either go down the TIG welding route or the MIG welding route. And again, this all very much depends upon what you want to do. I would say if you're going to go down the TIG welding route, then really you could do with a MIG welder and a TIG welder, because I find a MIG welder invaluable for doing things like plug welds, attaching complete panels to something else where you're going to have to plug weld it on, or do a little stitch weld or something. Then I still find a MIG welder invaluable for those kinds of processes. And if you're going to go down that road, then maybe you want to invest in both. And like I was saying, it's all about you. How do you operate as a person? It's all getting a bit deep now, but say I want to buy a new camera. So I want to buy a new camera, or I want to buy a new guitar, or any of the other things, you know, computer bits and pieces and all the rest of the stuff that I'm interested in, a nice bit of kit, you know, new paint guns or anything. I research things relentlessly. So I research all the characteristics of that, you know, that device or whatever it is I want, and then when I get it, I mean, I'm the only person I know with masses of patience. Most of the people I know haven't got patience. And when people say, how do you do that? I could never do that. It's, you know, it's like anything. It's like playing a musical instrument. People listen to somebody playing a musical instrument. I give anything to be able to play like that. Well, you could, but you got to put the practice in first. It's no good just picking something up and expecting it to work the way you would expect it to work. So, you know, the first thing you find out when you do anything that you're not used to doing is it's different from how I expected it to be. And this is very much the case of welding. You watch a video on somebody welding and you think, oh, that looks great, I'll go and buy that welder and do that. And then you start doing it yourself and you suddenly realise this thing doesn't work how I expected it to work, you know. So are you the kind of person that's got infinite patience and is happy to mess a lot of things up before they get to the, you know, the desired result? Then if you are, then maybe you ought to think about TIG welding and MIG welding. So you can have both if you wanted to. If you're on a massively tight budget and you're just going down the road of the car that's been made out of pressed steel panels and the panels are available and you just want to put a little patch in, then maybe a MIG welder will suffice. Only you can answer the question. But what I would say is, when you're MIG welding things, especially when you're tack welding like I've shown you, you're not really engaged in the welding process itself. I could get somebody to come along and I could set up a couple of bits of metal and I could have them tacking the metal together as good as I did earlier in an hour, no problem. I could show them how to set the welder up and they'd be able to do that, and it would look just as good as I'd done in an hour if it was MIG welding. Because like I say, you're not really engaged in the welding process. When we're talking about TIG welding, you've got a vast array of settings on the TIG weld: up slope, down slope, arc force, pulse width, pulse frequency, amperage, whether it's on AC, DC, gas flow, what cup size do I use, which tungsten do I use, what diameter tungsten, how do I sharpen the tip on the end, what degree angle do I put on the tip, how much tip do I have hanging out, and all these things will influence how the welder works before you've even started welding. If it's not set up exactly right, then you're going to pull the trigger back and it's not going to behave in the way you want it to. And there's also the business of being able to see the puddle weld, the weld puddle forming and everything else, and being able to control that and knowing what you're doing. Whereas when you're MIG welding, basically I could MIG weld, like, not that I ever have, but you know, I could just sort of pull the trigger and look away. Bzzzt. Oh yeah, look, perfect spot on that. And that's the difference between MIG welding and TIG welding in a nutshell, I would say, personally. So I hope that kind of points you in the right direction. I'm definitely not going to tell you what kind of welder to run off and buy, because it's all about you. What do you want? And what car are you doing? What project are you doing? How do you want it to come out? And how competent are you at patience? It's all about patience, you see. I'll show you a couple of bits of up here somewhere. A couple of little bits of stuff that I've TIG welded, because I haven't really done any videos on TIG welding. There's a very good reason for that. I ain't got one, but we got one at work that I use, and I've had some pretty stunning results from it. But getting back to something else I have forgotten to say, which I was supposed to say really, is that I do know two guys now that have gone off and bought TIG welders, and unfortunately they've given up because they just couldn't grasp, they couldn't master, they maybe didn't have the patience or whatever you really could do with somebody showing you, as I have had somebody that's you know, shown me the way that's totally invaluable. And I know there are a lot of companies that sell welders that they'll actually show you how to set the welder up. So this is really good advice, guys, and I think it's worth taking this bit of advice. If you're going to buy something like a TIG welder, then it's worth taking the time out to get a bit of training on it. And like I say, a lot of these companies that sell welders will actually, they'll say, come along and we'll show you how to set the welder up and everything else. And this is invaluable. It's all very well watching YouTube videos on how to do things, but sometimes you just need somebody to reach across and say, hey, just turn that dial down a little bit, you know, you just need that bit of extra help. So I'll show you a couple of these welding samples that I've done, so you can kind of get a grasp of the difference between MIG and TIG, because TIG's more kind of along the lines of gas welding, really, oxygen acetylene welding, where it's heating it up until the two pieces of metal are fusing together, and you can add filler rod to it as well. And you'll be looking at, say, on a TIG weld, you'd be looking at, I typically weld 20 gauge about 19 to 22 amps for 20 gauge. Now compare that to a MIG welder, you'd be poking in about 60 amps. So because you've got that filler rod coming out all the time, the welder needs to operate at a much higher amperage, because the rod's coming out, no heat in the panel, so the rod's coming out, it's hitting the panel, having to arc and melt and fuse the two panels together all in a split second. There's none of this heating things up till you get the weld puddle forming and then poking a little bit of filler rod in like you would do with TIG welding. So when you do TIG welding, you need much less power than you do a MIG welder, and this is why a MIG welder creates the distortion it does. I'm going to shut up for a minute and I'll just show you these panels, and then we'll move on. So here's some 1.2 mil thick aluminium sheet that I've TIG welded together. I don't think I actually used any filler rod on this at all, so I would have welded it on the vertical, and then gravity pulled the weld down. The weld hasn't sank back in any. You can just see where I've had a weld pull going, and then what I've done up here is I've just cleaned it up with a surface conditioning disc on a roll-up tool, just to polish it up, just to show you how, you know, that's really nice and flush. Now the back side is, you've still got a tiny little joint down the back that hasn't quite fused together. I find this quite usual when I'm welding with no gap at all. What we normally do is weld down on one side, make sure that we can get to the reverse side. If we can get to the reverse side, it's even quicker. Then we just run down there ever so quickly, and it just knits that little gap back together again. Not gap, just the two pieces that haven't quite knitted together right on the end, and it just knits those together, just running the welder down the back. If there's no access to the back, then normally leave a bit of a gap and then use a filler rod along it as well, and then it penetrates all the way through to the other side. So 20 gauge mild steel TIG welded together, just roll locked it off. So that's it, guys. Beautiful weld. You can't really see it. I've roll locked it off. I haven't ground that at all. 100% have not ground that. I've just literally welded it on the vertical. I did this just to set the welder up, so I was happy before I turned it onto the car that I was welding up, and I've just basically welded it from top to bottom. Probably, you know, put a couple of little tacks, and then sort of did a series of 20 mil 30 mil runs, just join them up together. And the back side, we can see a tiny little bead where it's just knitted together nicely as well. So that back's knitted together perfectly, unlike the aluminium. But the aluminium is 1.2 thick as well, and I think maybe that's got some bearing on that as well. So yeah, very nice. If you can get into TIG welding, you will generate greater finesse within your work. There's no doubt about it. But you've got to put the time in, guys. You have to put the time in. I'm going to wrap this up now because this is probably going to be the longest video in history. Perhaps I should have spread it out over two different parts. But the thing is, you see, it'd be nice just to guide somebody to one video and say, you know, the question you asked is in this video, and then they can just watch it and get the answers that they're after, which is what it's all been about. If you'd like to leave a comment about what you think. I mean, a lot of people I know that are in the trade watch these videos, and some like to chip away and some like to actually put some input, and the input's great. I remember doing a filler one once, and a guy said, I hope you don't mind me asking, but this is what I do. Oh no mate, you plaster it on there, because the more info we get down, the more, you know, people read through the comments, and they're going to read your comments and they're going to get something off your comment. So if it's useful, please put it on, and if it isn't, then you know, if it's not helpful, then, you know, hey you get your damn hands off her. I don't know why I felt the need to do a Marty McFly impression. Not Marty McFly, George McFly. Hey, you're George McFly. Yeah, see you guys. Bye for now. See you next time around.